In this video, we'll wire everything together, and in the next video, we'll fire it up, check everything out, and then jog the motor. Here we go. I'm using this servo drive, and I'm using single-phase 120 volt AC. This wiring will also work for 220 volt single phase. Wiring for 3-phase is similar. There's diagrams in the product insert that show both single and 3-phase power wirings. I'll add the power wires to this connector and plug it in. Now it's important to understand that this connector only powers the drive's control electronics. These guys power the output stage that drives the motor via this cable. I've already crimped ferrules onto these wires, so I'm just going to shove the U wire into the U hole and the V wire into the V hole and the W wire into its hole and insert this power connector into the drive. And I'll connect the ground wire. I love these spring clamp terminals. You can just shove ferruled wires in and you're guaranteed a tight connection, and you don't have to worry about getting screws at exactly the right torque or worry about them ever getting loose. They're maintenance free. I see in the drive's product insert that for this drive and motor combination, we should be using between 24 and 12 gauge wire for all power connections. And below that chart, we see what ferrule sizes we should be using for the different gauge wires. This product insert comes with a drive, and it's a really handy thing to have around. If you misplace it, you can always download it for free at AutomationDirect.com. Now we're going to leave the motor end of this cable unplugged until we've verified everything's correct. Notice I'm using the flex version of this cable. I like this version because it's more durable and it holds up better to continuous flexing applications. If I hold them side by side, you can see why. The flex cable has a lot more and finer strands of wire, which prevents corkscrewing the cable in the cable carrier, which helps it last longer. While we're here, I'll plug this encoder cable into the motor here and the drive here. Now you have two ways to power the drive's output stage. First, you can bring in power through the usual magnetic contactor here and build a ceiling control circuit with a momentary normally open on switch, which will allow current to flow through a normally closed off switch, and through a magnetic contactor's coil, which closes this ceiling contact, which keeps current flowing after you release the momentary on switch. And you would normally put a surge protection device across that coil to protect your system. The current then flows through a normally closed alarm contact, which the drive will open if it sees a fault via output pin 5, where you connect an external alarm relay that controls that alarm contact. So current's flowing through the control circuit like this, which keeps the contactor closed and power flowing to the servo motor. If someone opens the off switch or the servo system generates a fault, the current stops flowing and the power to the motor shuts down. The servo control electronics are still running, but the power to the motor is cut off. Now that's the first option for controlling the motor power. And it's important to understand that all of this is external components that you supply, wire, and maintain. Depending on your application, you may not want to remove the RST power because the motor is no longer being controlled by the drive and it will be left to coast to a stop, which could possibly damage equipment or even harm personnel. The second method of powering the drive's output deletes all of this external hardware, so now power is always applied to the output stage. And we just add a single toggle switch on input D1 and have it act as an enable for the output stage. I'm wiring it like this because this is the drive's default, but you can also wire this as a PMP connection. This common is a dedicated digital I/O common. Make sure you use that one with the digital I/Os. Safety is handled by adding a single STO safety relay at connector CN10. Now the built-in STO function disables the drive's output when there's a fault. We'll learn how to set up the STO in a separate video, so for now, we'll just take this pre-wired jumper that comes with the drive and plug it in CN10. That bypasses the STO function, which for our little test setup is fine because we aren't actually connected to a machine that requires a safety shutoff. On the control electronics power connector, there are 3 additional pins. I'm going to move those down here. Those are used to bypass the internal braking and add an external braking unit. We'll cover braking in a separate video, so for now, we just want to short these 2 pins. And the good news is, the connector for that port comes with the jumper already installed, so we don't have to do anything here. The last connector is where you add a braking resistor. We'll cover that in a separate video, so for now we just want to bypass it. And guess what? That connector also comes pre-wired with the bypass jumper, so we just plug that in here. Finally, I added a normally open switch to reset alarms and a normally closed switch so we can test the motor override. Think of that as a simplified e-stop, but without all the required safety stuff. Now, we don't have over-travel limits because we don't have a real machine. So I just wired them like this to simulate their normally closed operation to prevent them from generating faults. The I/Os come out through this connector, so I'll plug this cable in here and the other end into this breakout box where I've already wired up all those switches. This USB port is used with the SureServo2 Pro configuration software, which is amazing. It makes configuring and debugging your drive a breeze. You can download that right now for free at AutomationDirect.com. The RJ45 port is a serial port. It's not an Ethernet port. The cool thing about that is you can use any RJ45 Ethernet patch cord to wire your serial comms. Check out the Modbus RTU video to see an example of that. Well, this is what it looks like all wired up. And while I'm going from the drive through this cable to take the signals to this remote terminal breakout board, the SureServo2 also has this local terminal block option. The terminals are labeled on both the connector housing and these green terminal blocks, which unplug for easy access. It just plugs directly into the drive, and it's really convenient for those times when you just need a few I/O or you're controlling the drive primarily via comms. And while I'm talking about handy tools, the drive and connector kit comes with a couple of these guys. If you use ferrules in your wires, you can just press them into place. No tools required. Super easy, super reliable. But if you need to use loose wires, this little tool just clamps on like this. Then you press here to hold open the jaws of the spring clamp. Insert your wire, let go. Pop it off, and you're done. Hang on to those guys. They make installing stranded wires so much easier than trying to hold the spring clamp open with a screwdriver in one hand while you try to insert the wire with the other. I also appreciate that they give you two to make it easy to install jumpers. And that's it. Now, I did a lot of explaining in this video, but if you think about it, all we did was wire up power to two places, connected the motor's encoder, and almost connected the motor. We're saving that for part 2. We then plugged in all the pre-wired jumpers and added some toggle switches and an external 24-volt supply. I also added a circuit breaker here. Not bad at all. I'll put a link to this diagram and the parts list in the description below this video. Join me in part 2, where we'll fire this thing up, test everything, and finally plug the motor in and jog it. Meanwhile, click here to learn more about the SureServo2 system from Automation Direct. Click here to subscribe to our YouTube channel so you'll be notified when we publish more videos like this, and click here to learn all about Automation Direct's free award-winning support options.